So we'll talk about a mathematical induction. Let's start with the following example. Suppose that we would like to know what would be the sum of the first n odd integers. Like, the first odd integer, for example, is 1, then you have 3. So these are the first two. Then you have 5, then 7, and so on. According to this, the last number is going to be 2n. Well, it's going to be either -1 or +1, but let's count it here. So this is like 2 times n minus 1, because when I'm starting with n equal 1, so if n is equal to 1, this is going to give me 1. So this is from here to here. I have the first n odd numbers. So I would like to know what would be the sum of all these numbers. Like, for example, look, when n is equal to 1, I get 2 times n minus 1. An odd number can be 2n minus 1 or 2n plus 1. You can write whatever you want. But for this, I'm going to have 2n minus 1 because I'm looking for the first n odd numbers. And if I start with 1, so 1 will be represented by 2n minus 1. Since I will let n starts at 1. So when n equal 1, I get 2n minus 1 becomes 2 times 1 minus 1, which is 1. When n equal 2, I get 2 times n minus 1 equal 2 times 2 minus 1, which is 3, and so on. So you can see this when n equal 1, this is when n equal 2, and so on. So when n is n, after n numbers, if I plug in n, I'm going to get 2n minus 1. So the goal is to find the sum of the first odd numbers, see if this is possible or not. So to do this, we will try first to add up some examples. Okay, so this is the first odd number. You cannot add it with anything. So if I'm just adding the first odd number, that's going to be just the same number. If I'm adding the first two odd numbers, 1 plus 3, I get 4. If I'm adding the first three odd numbers, 1 plus 3 plus 5, I get 9. If I'm adding the first four odd numbers, I get 16, and so on. Do we have any pattern here? Well, if you look at the numbers that I have on the right-hand side of each of these equations, you can see that, for example, this is 1, okay, this is 4, but 4 is 2 square, 9 is 3 square, 16 is 4 square, 25 is 5 square, and notice here, this is the sum of the first 5 odd integers, okay, and so on. So it seems that I do have some sort of a pattern here, that the sum of the first two odd numbers is 2 square. The sum of the first three odd numbers is 3 square. Like here, the sum of the first 6 odd numbers is 6 square. And the sum of the first 7 odd numbers is 7 square. So I do have some sort of a formula here. But is this enough to claim that this is gonna work? Like here, we said before in the class, you cannot prove something by using examples. You need to do this in general, okay? So here I took some examples. I took 6, 7 examples, but this is not enough, okay? We need to prove this for an arbitrary n. So that's the main question. Can we be sure that this is valid? Because here it seems that the sum of the first n odd integers is n squared. I want to prove this claim. But again, we cannot prove this by examples. We need a new tool. I want to rephrase the problem. So I want to call each of these equations that I had in the previous slide as a statement. I'm going to call them S1, S2, and so on. So I'm given a statement here, and you can see that this is Sn. So this is the sum of the first n integers, and I'm saying that this is n squared. I didn't prove this yet. That's what I want to show. Okay. Now, why I want to show this? Because by looking at the examples, I saw that there's some sort of a pattern, and now I would like to show that this is true. Okay. So the main question is, are all these statements true? Well, these ones were true. We were able to check, but this one, I don't know yet. Okay, because here I'm talking in general. Is this going to be true if n is equal to 1000 or 1 million, for example? Okay. So the new tool that we will use is called mathematical induction. So mathematical induction is designed to answer questions of this type. Okay. The method is not complicated. It's very similar. To visualize it, I want you to look at the next slide, and this is we're gonna relate this to falling dominoes. Okay, so here's the idea. We're gonna call each statement S1. Okay, S1. The statement is gonna symbolize as domino S1, which is the first domino that will be knocked down. Additionally, imagine that you can prove that any statement Sk being true forces the next statement Sk plus 1 to being true. What does this mean? This means that you have a set of dominoes. Okay? If you show that domino Sk and next to domino Sk plus 1 and so on, and of course you start with domino S1. You know that S1 is true. If I want to relate this to domino, that means S1 is gonna fall. Now, if I can show that if for any k I pick, if Sk fall will force Sk plus 1 to fall, then I can conclude that all the dominoes will fall. Now, if I want to relate this to my statement, when I say a domino will fall, that means a statement is true. So the idea is this. If I know that S1 is a true statement, and if I know that if Sk is true, that means if the domino Sk is gonna fall, then domino Sk plus 1 is gonna fall, then Sk plus 1 as a statement is true. If I can do this, if I can show these two things, the first domino is gonna fall, and any domino that falls must force the next domino to fall, that means all the dominoes are gonna fall. And if I relate this to the statements, this can be translated as follow. If S1 is true, and if I can show that if Sk true, then I can show that Sk plus 1 is true, then this means what? This means that Sn is true for all n. This is the idea of proof by induction. And here's a figure that's gonna summarize the idea. So these are all the dominoes lined up. Again, the dominoes are the same as the statement. Suppose that the first statement falls, which means suppose that the first statement is proved to be true. Then S1 is gonna knock S2. But I don't know that if S2 is gonna fall or no or no yet. Here's what I need to show. So the first step, I need to show that the first domino is gonna fall, which means that the first statement is true. The second idea is that I'm gonna pick an arbitrary number k, integer k, and I will assume that the kth domino is gonna fall. So if Sk is gonna fall, Sk is gonna hit Sk plus 1. If I can show that Sk plus 1 is gonna fall, then all the dominoes will fall. So if I can show that if Sk is true, then Sk plus 1 is true as a statement, then all the statements will be true. And this will be the method that we call proof by induction. To illustrate this idea, well, before giving an example, to illustrate this idea, I'm going to show you the steps that we will follow. We're going to have a statement that we want to show. We're going to call this statement S of n or P of n or whatever you want. Then we're going to do two things. We're going to prove that S1 is true, and usually this is very simple. So you want to show that this is what we call the base case. You want to show that the base case is correct. Like if you now it's not always the case that you start with n equal 1, but if I'm starting with n equal 1, then I'm going to show that S1 is true. Now, given any integer k, so k is a random integer, we're going to prove that if Sk is true, then Sk plus 1 is true. If I can do these two steps, then the statement is true for all n. Now the first step is quite easy. The second one is the one that needs some work. So this is a bit harder, as you will see. Okay, so step one is called the basis step, and this is very important. You have to write the solution like I write it in the next examples. So first, you can start by defining Sn, and then you want to say the basis step, and in the basis step, you need to do what? You need to show that S1 is true. This is usually very simple. Then we move to the second step. We call it the inductive step. The second step is called the inductive step. Well, in the inductive step, we will use mostly direct proofs. Okay, so direct proof is most often used to prove this conditional. Sk implies Sk plus 1. So again, here we assume that Sk is true. And we want to show that S sub k plus 1 is true. Now, when you assume that Sk is true, this is called the induction hypothesis. Okay, we call this the induction hypothesis. It's already written here. So this assumption is called the induction hypothesis. And this is going to be the key to show that S sub k plus 1 is true. Let's begin by trying this example. Prove by induction. Induction is the same as saying mathematical induction, that the sum of the first n positive integers is n times n plus 1 over 2. What does this mean? Well, let's see. The first n positive integers, the first one positive integer is 1. Or let's define this. Let Sn be, or Pn here, because I'm using Pn for this example, be the following statement, that 1 plus 2 plus n. So this is the sum of the first n positive integers. I want to show that this is equal to this. So this is the statement Pn that I want to show, like Sk or Sn in the previous definition. So the base case here starts with 1. I start with having one positive integer. So let's just write what this means. P of 1 means that 1 is equal to 1 times 1 plus 1 over 2. Is this true? Well, this is clearly true because the right hand side is 2 over 2. P of 2 means what? You don't have to do P of 2, P of 3, but this is just, you can see what I mean by this. The sum of the first two integers. I'm not trying to answer the first example I asked, which is the sum of the odd integers. I'm just doing something a bit simpler here. So 1 plus 2 is what? It's n is equal to 2. So let's replace 2 here and see if we're going to get the same answer. So on the right hand side, I get 3. Here I get 2 times 3 over 2, which is also 3 as well. So this is fine. P of 3 means 1 plus 2 plus 3. And here replace 3 on the right hand side. You get 3 times 3 plus 1 over 2. Over here you get 6. Over here you get 3 times 4, 12 over 2 is also 6. So this is true. But this is not enough, as we said. We need to show this in general. So here's how we write this nicely, and here's how we prove by induction. First, you have to define this like I did. So you let P of n be the statement 1 plus 2 plus etc. up to n is equal to n times n plus 1 over 2 for n greater or equal to 1. So when you say n is greater or equal to 1, this automatically implies that the base case or the basis step is P of 1. So when I want to show the base step, I will consider P of 1. So the base step here is P of 1 is true. Now the reason why P of 1 is true, because if you replace 1 on the left hand side, then the sum is going to carry only one number, which is 1. And the right hand side is going to be what? 1 plus 1 times 1 plus 1 over 2, which is 1 as well. We showed this. This is true also. We verified P of 2, P of 3, but that's not necessary. Only one, only proving that the first domino is gonna fall, that the first statement is gonna fall, is true, is enough. Now comes the inductive step. You assume, and this is very important, you have to write the problems in this format. You assume that P of k holds for an arbitrary positive integer k. What does this mean? This means that you are assuming P of k is true for some integer k. I don't know what's k. But what does P of k means? Instead of n here, put k. So that means that the sum of the first k integers, so 1 plus 2 plus etc. up to k, should be equal to k times k plus 1 over 2. Now, under this assumption, so this is right here, is the what we call the induction hypothesis. And you have to use this to be able to prove P of k plus 1. So I'm assuming that P of k is true. Now I want to show that P of k plus 1 is true as well. And I always recommend to write what you want to show. I want to show this. Okay? I don't have it. That's what I need to show. Okay? So I want to show this statement, and I have to make use of the induction hypothesis. So let's take a look at the left-hand side. As I said, I'm going to show that this is equal to this. I'm starting from the left-hand side, and I hope that I will be able to reach the right-hand side. Now, the left-hand side is 1 plus 2 plus k up to k plus 1. Now, we want to rearrange the terms. So I'm taking these terms together. Now, the reason behind this, why I want to take these terms together, because the ones I have here written in blue are exactly those ones right here. And these ones, by the induction hypothesis, can be substituted by k times k plus 1 over 2. That's the idea. So instead of all these, I'm going to substitute them by k times k plus 1 over 2. Now, on the right-hand side, I have this plus k plus 1. You can factor out k plus 1 from here and k plus 1 from here. You end up with k over 2 plus 1, common denominator. This leads to the following. And that's exactly what I wanted to show. So I started from here, the left-hand side, and I was able to reach the right-hand side. So this is enough. This shows what? This shows that I assumed that P of k is true, and I showed that P of k plus 1 is true as well. And this completes the inductive step. As a result, P of n is true for all n. Now, back to the problem that we stated at the beginning. So prove by induction that the sum of the first n odd positive integers is n squared. So I'm going to let P of n be the statement 1 plus 2, 1 plus 3 plus 4 plus 5, etc. up to 2n minus 1. So from here to here I have n numbers and n odd numbers. I want to show that this is equal to n squared for n greater or equal to 1. So starting with the basis step. So the basis step is P of 1 is true. So I need to show that P of 1 is true. Is this true? Again, as I said, usually this is very simple. If I want to show that P of 1 is true, then let's write what's P of 1. P of 1 means this. Here I'm going to have, instead of n, 1, so 1 squared. On the right hand side, I'm going to stop at 1, because when n is equal to 1, that number right here is 2 times 1 minus 1, which is 1. So I'm going to just stop here. 1. Is 1 equal to 1 squared? Yes. So this is done. The basis step is correct. Now is the inductive step. In the inductive step, you assume that P of k is true for some integer k. Now, what does it mean to say that P of k is true for some integer k? This means that 1 plus 3 plus 5, etc., up to 2k minus 1 is equal to k squared. This is something I have, and this is what we call the induction hypothesis. And I want to show that P of k plus 1 is true. And I always like to write the equation that I want to show. So in other words, I want to show this. To show that 1 plus 3 plus 5 plus 2k minus 1 plus 2 times k plus 1 minus 1. So I'm adding equal k plus 1 square. So this is what I want to show. Okay. So for k, you put k here. For k plus 1, you stop when this guy is k plus 1. Okay. Now, when you want to show an identity or you want to show like two things are equal, usually you start from the side that looks much more complicated. And certainly the left-hand side is more complicated here. So starting from the left-hand side, this is equal to 1 plus 3 plus 5, etc. 2k minus 1, and you stop here. 2 times k plus 1 minus 1 equal. Now, in the process, you have to make use of the induction hypothesis, this equation that's written in this box. Okay, well, notice something here, that this sum from here to here is exactly the one in the induction hypothesis. So this can be replaced by k squared. The reason is by the induction hypothesis. So the sum 1 plus 3 up to 2k minus 1 is k squared. I'm not done yet because I'm still have some left over here. And let me write what's this. This is 2 times k plus 2 minus 1. So basically this is k squared plus 2k plus 1. And the good news is that this can be factored. That's a perfect square. This is k plus 1 squared. And that's the right hand side. You see it? It's right here. That's what I wanted to show. So the proof is done, and this means what? This means that P of k plus 1 is true. So I showed that if I assume that P of k is true, I was able to show that P of k plus 1 is true. Then you write the following statement. Then by mathematical induction, P of n is true for all n greater or equal to 1. So this is how you show, and this is how you write nicely a proof by mathematical induction. This is an exercise. You should be able to try it. Try to do it. It's not too hard. I want to do something related to divisibility here. This is a pretty it's not too hard, but lots of algebra. So I want to show by induction that 5 divides n to the power 5 minus n. You know, if I don't want to use mathematical induction, this problem is very simple. If I use modular arithmetic, I will let you think about it. You can ask me, but this is very, like, this takes like maybe 1 minute to be done by modular arithmetic. Now I want to do this using mathematical induction. So first I have to define my statement. So let P of n, so that's my statement right now. It denotes that 5 divides n to the power 5 minus n. When n is a positive integer, so actually here I have a typo. This should be when n is greater or equal to 1. So when n is equal to 1, you're gonna have 5 divides. So P of 1 means 5 divides 1 to the power 5 minus 1. 5 divides 0. Yes, any number divides 0. So this is true. Okay, since every integer divides 0. Now comes the inductive step. Let k belongs to z. So k is an arbitrary integer such that k is greater, or I mean, even if k is equal to 0, that's the proof is gonna work. But because I stated positive integers, then this type was scared away. So this is always 1. Assume that p of k is true. That is, assume that 5 divides k5 minus k. Now this assumption is the induction hypothesis, and this is the key always. This is the key to solve each problem. Now we must prove that p of k plus 1 is true. That means you must prove this. So this is what you need to show. I don't have this, that's what I seek. Okay. Now to prove this, I need to show the following. I need to show that 5 divides this guy, I need to show that k plus 1 to the power 5 minus k plus 1 is equal to 5 times some integer. That's the definition of divisibility. So this is my goal. Okay, so you have to keep this in mind. That's my goal. So it will make sense now to start from the left hand side and try to write this as 5 times something. Okay, so simplify the expression k plus 1 to the power 5 minus k plus 1. As I said, lots of algebra done here to expand k plus 1 to the power 5. But once you expand it and you collect like terms, so k plus 1 to the power 5 minus k plus 1 is just this. Okay. This is just algebra, expand, collect like terms. I'm leaving this hard work for you to verify that this is correct. But remember, as I mentioned earlier, that my goal is to show that this is equal to 5 times something. I don't see any 5 here that I can factor out. But remember, I said always the key is to use the induction hypothesis. Now the induction hypothesis says what? Says that 5 divides k to the power 5 minus k, which means k to the power 5 minus k is equal to 5 times some integer. Let's call it a. This is some integer. Okay, now do I have k5 minus k here? No, I don't. So what do we do in this case? I do have k5 by itself. Do you see it? I need to get some minus k. To get this minus k, I'm using the following trick. Instead of writing 4k, I'm gonna write 5k minus k. It's not gonna change anything, but it's just writing this in a different way so that I can generate the missing minus k I need. But this is gonna be very helpful, as you will see. Now, let's rearrange the terms. I'm gonna make negative k next to k5 and group them together. And what's left is this term, 5k4, you can see it here, 10k cubed, you can see it here, 10k squared, you can see it here, and the 5k, you can see it here as well. Now, by the induction hypothesis, I know that k to the power 5 minus k, this guy, can be written as 5 multiplied by a, where a is an integer. Okay, so k5 minus k is written as 5a, and everything else here is left the same. But there's something nice you should see on the right hand side now, that all the terms are multiples of 5. So I can factor out the 5 that I was looking for. And this guy right here is an integer. That's what I want to show. I wanted to show that k plus 1 to the power 5 minus k plus 1 is equal to 5 multiplied by some integer. And here's what I have. So to finish this, we say that since this is an integer, then 5 divides this. So p of k plus 1 is true. And because p of k plus 1 is true now, I can say that p of n is true. It doesn't show here. So p of n is true. So then p of n is true for all n greater or equal to 1. Or greater or equal to 0. It works as well. Let's do another example. Well, this is similar to that previous one, so I will not go over it, but you can just read this solution on the slides. I recommend you try it before you do the solution. It's very similar to the problem we just did. Another divisibility problem. I want to show that 5 to the power n minus 1 is divisible by 4. Here I'm showing you this because the trick is different than the previous one. Again, by modular arithmetic, this is easy because I think I should show you this. Just a note on the side, okay? Using modular arithmetic, chapter 4, 5 to the power n minus 1 is congruent to what mod 4? Well, let's see. If I reduce 5 mod 4, that's going to be 1 to the power n, and this is going to be minus 1. So this is congruent to 0 mod 4, and I'm done. Because any number congruent to 0 mod 4 is divisible by 4. So that means that 4 divides 5n minus 1, and this is done. You see, some stuff in modular arithmetic are really simple, but this is a problem. The main thing of here is to get used to mathematical induction. So I want to show you how I can do this using mathematical induction. Again, like usual, I'm going to define a statement. I'm going to call it P of n. That statement means that 5 to the power n minus 1 is divisible by 4. Or if you want, you can say 4 divides 5 to the power n minus 1. It's the same thing. So first, I need to show that P of 1 is true. Okay. So to show that P of 1 is true, you plug in 1 for n. And when you plug in 1 for n, you get 5 to the power 1 minus 1. And this is clearly 4. Is 4 divisible by 4? Yes. Basis step is true. Now, I move to the inductive step. I start by assuming that P of k is true for some integer k greater or equal to 1. This means what? This means that 5 to the power k minus 1 is divisible by 4. What does this mean? What does it mean to say 5 to the power k minus 1 is divisible by 4? This means here, just note on the side. Okay, so this, the red statement means that 5 to the power k minus 1 is equal to 4 times a, where a is an integer. Now we must show that P of k plus 1 is true. That means we must show this. So this is your goal. That's what you need to reach. Okay. Now, the logical thing is to try to start from 5 to the power k plus 1 minus 1. And your goal is to write this as 4 times something. Now, I'm writing 5 to the power k plus 1 minus 1. You cannot do proof by induction without using the induction hypothesis, which is this assumption right here. So somehow you need to create 5 to the power k. So I know that 5 to the power k plus 1 can be written as 5 to the power 1 multiplied by 5 to the power k. Okay, but I need 5 to the power k minus 1 to be together. So that's the trick. Instead of 5, I write 4 plus 1. Why this is helpful? Now expand. 4 times 5 to the power k is 4 times 5 to the power k, as you can see here. Now 1 times 5 to the power k is 5 to the power k minus 1. So I was able to get that form, 5 to the power k minus 1. And this is what? This is 4a. Okay, so 5 to the power k plus 1 minus 1, that guy, is equal to 4 times 5 to the power k, the one that we have here, we just carry it down. And this becomes 4a. We are writing 4a instead of 5 to the power k minus 1. Factor out the 4. Okay, you can clearly see that I have a typo here, so that should be 4. So this becomes 4 times 5 to the power k plus a, and that's the integer that I'm looking for. So 5 to the power k plus a belongs to z. That means 5 to the power k plus 1 minus 1 is divisible by 4, so the proof is done. And that means that P of n is true for every n greater or equal to 1.